Okay, today we will see Euler's equation of motion. See, although all this basic fluid mechanics you have been exposed during your undergraduate study, some of these equations will be mentioned, and it is always good to have brushing up of your fundamentals. This is the purpose of having this as a part of the syllabus of wave hydrodynamics. So let us proceed with Euler's equation of motion. In the earlier class we had seen what are all the different kinds of forces, and then the corresponding equations also we have seen. Finally it boiled down to Euler's equation of motion, and in this case we consider only the pressure forces and the fluid weight, or in general the body force. They are assumed to be acting on the mass of the fluid in motion. I will just draw this figure so that it will be easy when we are referring to just make it slightly bigger. So this is x, y, z. So this will be, the length is delta x, and this is delta z, and let me have this point q, this will be r dash, then this is s, so this will be r, this will be q dash, this will be p dash, this should be s dash. No, I think let it be, this be point P, so in this case I think so we consider a point at this location, and then we in the flowing mass of fluid, and let us say that u, v and w are the velocity components in the x, y, z directions respectively. Rho is the mass density, and let P be the pressure intensity. P is pressure intensity. So we define x, y, z are as your body force components in the x, y, z directions, and let this be the components of the body force per unit mass. So now the mass of the fluid in the fluid medium would be volume into the mass density. So that will be the mass of the fluid in the fluid medium, and then now the total component of the body force will be, in the x direction it would be x into the mass density, the mass, so x into, so you will have multiplied by x, that will be the total component of the body force acting in the x direction. Similarly, you have in the y direction as well as z direction, and P, as I said earlier, is the pressure intensity at point P. Since the length of the edges of the fluid medium are extremely small, let us assume, or it may be easy to assume that on this surface, over the entire surface, R, S, P and Q, that is this phase. Let the pressure intensity be uniform as defined as small p. Okay. So, what will be the pressure force acting on this surface? This will be P into the area of this, which will be delta y into delta z. Okay. Now, P varies with respect to in both in all the three directions x, y and z. So, the rate, the pressure intensity on the phase R, S dash, P dash and Q dash. So, that is this phase So, this phase will be P, that is the initial pressure, the pressure changing over x over a distance of delta x. So, that will be the, that is the reason why you have P plus dou P by dou x over a distance of delta x. But this is the pressure intensity on this phase. So, similarly you have to get the pressure force on that phase, which means this pressure intensity multiplied the area, that is what is clearly defined here. So, the total pressure force on this phase would be into is that clear? So, the net pressure force will be what? On this phase you have already evaluated and on this phase you have already evaluated, the difference has to be your pressure force. So, that is what is given here, the two pressure forces acting on both the surfaces. So, when you do that, the net force will be take the difference between these two, that will result in dou P by minus dou P by minus dou P by dou x into delta x delta y delta z. This will be the net pressure force. So, per unit volume will be, this will disappear and the net pressure force per unit volume for all the in the three directions are given as Fpx, Fpy and Fpz. Is that clear? Now, adding the pressure force with the body force. So, body force we had already, I have already explained, this is the body force and this is the pressure force. So, these two have to be added. What does that mean? That is Fp plus Fg equal to mass into acceleration, right. So, this is the total force into mass into acceleration. So, you remove the volume, so you get x minus 1 by dou dou p by dou x equal to Ax. So similarly you have in the other two directions y, z, etc. So this is actually called as your Euler's equation of motion. So the above equations in the three directions, these are called as the Euler's equation of motion. Now you see that there is a term Ax. What is this Ax? Ax is termed as the total acceleration. Total acceleration, when you want to define it in terms of the velocity components, although we know that it is a differential of velocity, it has two components, one is with respect to time and the other one is with respect to space. So wherever you have a, so in the x axis dou u by dou t plus all the terms with respect to space, and similarly Ay and Az. So here also you will have dou v by dou t, here you have dou w by dou t. So all these things are called as, these terms are called as local acceleration or temporal acceleration. So this are called as local acceleration or temporal acceleration, and whereas all the terms with respect to space are called as or termed as convective acceleration. So in these derivations, no assumption has been made concerning rho. Rho is retained. Since these equations naturally are applicable to compressible, incompressible, non-viscous fluid in both for steady or unsteady state of flow. Is that clear? Okay. So that shows, with this we have now derived the expression for Euler's equation of motion, but where and why Euler's equation and how are used, we will just understand with the help of a simple problem. One or two problems probably we will be able to see later. Now let us try to understand or recollect, it is not understanding, most of you should be knowing about all these things, it is only kind of recollecting what we have studied earlier. I will just run through this slide, I will not spend much of time because it is more or less quite fundamental. Path lines and streamlines. A path line is the trace made by a single particle within the fluid medium over a period of time, okay. It is the path. The path line shows naturally the direction of flow or direction of the velocity of the fluid particle at successive instants of time, how the particle is going to move. This can easily be understood when you want to have some kind of a flow visualization technique. You can easily look at how the different fluid particles can move also. Streamlines show the mean direction of a number of particles at the same instant of time, that is streamline. Now in case if you have a camera that has to take, that you are having a short time of exposure of a flow to a flow in which there are a number of particles, each particle will naturally show a short path or short or long path. It's its own path which would indicate its velocity during that period of time. Since I am saying that it is a short exposure, naturally you will be, the fluid particle will have moved only for over a short path. A series of curves drawn tangent to the means of velocity vectors are called as streamlines. So these are the definitions of path lines and streamlines. Path lines and streamlines are identical in a steady flow, in which there are no fluctuating velocity components. That means what we are trying to say is, in the case of a truly steady flow, the path line and streamline are going to be identical, and the equation for the streamline is given by u is the velocity in the direction x divided by the distance, okay, dx, elemental distance. So u divided by dx equal to v divided by dy equal to w divided by dz. Now velocity potential we will be seeing velocity potential, which will be the basic parameter or the variable which we will be considering for understanding the motions of a wave. That is, when a wave is moving, what happens under the waves, that is its kinematics, particular dynamics, etc. All these things are related to or derived from the velocity potential. So before going into all those details, first let us understand what is meant by velocity potential. Velocity potential is defined as a scalar function of space and time, such that its derivative with respect to a given direction or a particular direction yields the velocity in that direction. Hence in general, a direction s in which the velocity is vs. So dou phi by dou s equal to vs, where s is the general direction. So if you are considering a 2-dimensional flow, u is equal to dou phi by dou x and v equal to dou phi by dou y. As I said earlier, there are several books available on the net. There are several e-books also available, particularly on fluid mechanics. So you can refer to any of the books, and this only just to give you some idea. Now some of the books would consider this as minus. So when there is no harm in either representing this positive or negative, but when you are trying to be involved in solving a problem, make sure that you are consistent, either you use a negative sign or you use a positive sign for the velocity components. You cannot keep changing it. So we have already seen the continuity equation. So when you substitute for u and v, then you will have the del square phi equal to 0. So this is the equation, the equation for the continuity. So once you substitute for u and v, so you are going to get the Laplace equation, and this Laplace equation will be the base from which this will be actually the governing equation when you start deriving the expressions for the kinematics of a ocean wave. Now stream function again is called is a scalar function of both space and time, such that the partial derivative with respect to any direction gives the velocity at right angles to the I mean the counterclockwise direction to this direction. So what does this say? U equal to y, whereas v equal to, since we are talking about counterclockwise, there is going to be a negative sign for u. Again if you substitute this, you can prove that this is equal to 0 if you substitute in the continuity equation. Okay, I am sure that all these things have been already, you would have seen in your life, but during your undergraduate course. So now we will look at the Bernoulli equation. Why Bernoulli equation? The common example for the application of Bernoulli equation is when you have a pipeline and you have either it is tilted or it is horizontal, then you see that there is a flow taking place, pressure at one point is known, you want to know the pressure at the other end, or maybe you are interested in finding out what could be the pressure drop, etc. So it has a wide application in the field of particularly in the field of fluid mechanics. So let me start with force potential. I define a force potential as shown here, wherein x, y, z are represented as there, and u are also u, v, w in terms of velocity potential is also given there. Now substituting the Euler's equation and using the substituting all these things in the Euler's equation of motion, and also adopting the irrotational flow conditions, we can get a set of equations as shown here in the x direction, y direction and z direction. Here if the rho is the constant of rho is a constant, integration with respect to x, y, z, look at these expressions, you integrate these expressions, you will have half into u w v of course you have the time also. So for example in the x direction, this is a kind of expression you would have or equation. Okay. So what we are trying to do is Bernoulli equation, we are representing the force velocity potential, substituting these expressions in the Euler's equation we have derived, and at the same time you are also taking care of using the irrotational flow conditions. So once you do this, this is the kind of expression you will get, and once you get this, if rho is the constant of integration, integration of this expression would result in this expression. Basically what is Bernoulli equation? You integrate Euler's equation of motion and make sure that you are using irrotational flow conditions. That will yield you the Bernoulli equation. So, now if u, v and all these things are resolvents of v, then we can simply say call it as v, that is the velocity head or a velocity component. So, half into v square plus dou phi by dou t plus p by rho equal to, okay. In a general form you can represent the Bernoulli equation in this form. So, when you consider only steady flow, T will disappear. So, this will go only for steady flow. So, minus G equal to minus, if we also have that this acceleration due to gravity, okay, and this is with respect to elevation, then you can represent this as GH. So, now you substitute in this expression, you have the velocity head or the kinetic head, then you have the potential head which is now this one and plus the pressure head. Is that clear? So, this is what is called as your Bernoulli equation. Bernoulli equation is kinetic head plus potential head plus the pressure head is a constant. So, most of the applications, what will happen if you have a pipeline here, if this is inclined like this, then this will be your head, it is going to take care of the potential head. Suppose in case you have the velocity at this location as well as the pressure head at that location, and at this location you have the pressure head or one of the either the pressure head or the velocity head. Using the equation, the total energy is a constant at this location as well as at this location, the same thing will hold good. So, if all these things are available at location 1 and at location 2 this is not available but these are available, then you can determine this by equating the total energy on both the locations. So, in this way this becomes very handy in applying this for this kind of problems. So, naturally we will have one or two problems in order to again recollect whatever we have studied earlier. So, although there are a number of books available for the fluid mechanics, I have referred some of these books which I found has given very clearly the aspects of whatever the topics whatever I have covered. Now, let us look into this problem. This is basically to apply the Euler's equation of motion. The problem is, what is the problem? The rate at which the flow is taking place, that is the water is flowing, the rate at which the water flows through a horizontal 20 centimeters pipe is increased linearly from 30 to 150 liters per second. And within what time? In 4.5 seconds. What you are supposed to do? Get pressure gradient what is a pressure gradient that should exist to produce this kind of an acceleration. You understood? What is the pressure gradient for producing the above acceleration? What is the difference? What difference in pressure intensity will prevail between so the pipeline is there, so this is the kind of difference we are having. What is the now pressure difference in pressure? Naturally there will be a difference in the pressure intensity. So the next problem is what is the difference in pressure intensity that will prevail between any two sections 8 meters apart. Okay. So all these words are very important, particularly with respect to the position of the pipeline, okay, rate at which it is being pumped, all these things, because try to recollect the definitions of the different types of flows. What is a steady flow, what is the difference between steady flow and a uniform flow, etc. So when you look at such problems, these sentences really matter a lot. For example, in this problem, has anything been said about the pipeline? The pipeline can be horizontal or it can be inclined also. So or the pipeline can also be constant diameter or varying diameter, and in fact these were kinds of examples we took when we were telling about, when we were discussing about the different types of flow. So since the pipe is a constant diameter, since a constant diameter, what happens? Constant dia, naturally dou u by dou x will be equal to 0. Now since the pipeline is horizontal, that gives you another indication that the body force per unit volume is also 0, that is in the direction of wave flow, in the direction of flow. So we started this kind of an equation initially for the x direction, which is nothing but the Euler's equation of motion. So since it is equal to constant diameter, so this will be equal to 0. Next is, since it is horizontal, body force is going to be 0. Then you are left only with dou u by dou t equal to, so this takes care of, this gives you the relationship of the acceleration and the pressure gradient along the pipeline, and that is what you are interested in. So the changes in the velocity from 30 to 150 liters, what does that mean? you can get your delta u. So delta u, because the diameter of the pipeline is also known to you, so you can calculate the area, and velocity will be as shown here 150, that is the discharge, that is the discharge divided by your pi by 4 into your diameter square. So we are basically trying to get the area. So the velocity at the upper point, that is at the point where your discharge is more, minus the point at which the discharge is less, that is 30 liters per second. You have the 1000 to take care of the conversion. So you have a delta u will work out to 3.81 meter per second. But this acceleration is going to take place within within how much? Within 4.5 seconds. So from this, dou u by dou t is going to be 3.81 divided by 4.5. So dou u by dou t is going to be equal to 0.85. Okay. So now what we are supposed to calculate is the pressure gradient. So use the same expression. So you get the pressure gradient in terms of newtons as minus 847 newtons per meter square per meter. The pressure drop here is per meter, but what is the problem asking you? Is asking you to calculate the pressure drop over a distance of 8 meters, and that is going to be minus 6.77 kilonewtons per meter square. Okay. Is that clear? So now this is a classical problem which helps us understand the application of Euler's equation of motion. There are several such problems available in books. You may just go through them and try to familiarize yourself. It is very interesting. Any doubts? No doubts. Okay, we go on to the next problem. Here we are talking about the wind velocity in a cyclone. So the problem says the wind velocity in a cyclone may be assumed to follow the free vortex law. Free vortex law is look at some standard books for getting this details on the vortex law. If the velocity is 20 km/h, sixty kilometers from the center of the cyclone. So this is the center of the cyclone. We have a distance of 60 kilometers. That is the velocity we have. What reduction in the barometric pressure should occur over a radial distance 12 kilometers from this point towards the center? So this is 60 kilometers. So basically what we are needing 12 kilometers from this point. So this will be your 48 meters from the eye of the storm. So what reduction in the barometric pressure should occur over a radial distance 12 kilometers from this point towards the center of the storm. So basically you are trying to find out what is the kind of reduction in the barometric pressure. Is that clear? So in a we have already been told that it is going to follow this law. So now at a radial distance, let me take, there are two radial distance at 60 kilometers per hour, V1 is 20. So according to the law you can easily calculate C as 1200. I am not writing the units because anyway it is there on the slide. So velocity at, use the same equation for V2. So V2 will be CR by C by R2, since R is already determined. So you can get V2 as 25. Is that clear? So what is the velocity at this location? So at this location naturally your velocity should be more compared to this location because it is far away from the eye of the cyclone. So now you use, from Bernoulli equation we are considering the velocity and the pressure head equal to a constant. Okay, this is what the Bernoulli equation states, that is V plus rho into V square equal to constant. When you differentiate with respect to R, because we are interested in finding out the pressure variation in the along the radial direction. So when you do that, when you integrate this, you will equal to okay. Now we already know that this is the vortex formula. So when you derive this, I mean differentiate this from this, you can get dV by dr equal to V by R. Is that clear? So dP by dV or dP by dr, so you use this here, so you are going to get rho into V square by R. So this will be so the pressure gradient at a radial distance of 20 kilometers, where a distance of 60 kilometers, where the velocity is 60 kilometer 20 kilometers, then dP by dr, what is the pressure gradient? Use this expression. So you have the velocity, use the velocity here, and the radial distance is also known to you. Use the, so you will get 6.09 Newton per meter square per kilometer. Okay. So similarly, reduction in the barometric pressure over a distance 12 kilometers, that is within this distance. So R1 is already known to you, R2 is 48, R1 is 60, R2 is 48, V1 is equal to known to you. So all these values are known to you. Then use the Bernoulli equation. Bernoulli equation at these 2 points are applied as shown here. So the pressure gradient can be obtained. This is the pressure gradient. Use the corresponding velocities and you will get, this is the kind of reduction in the barometric pressure. You understood? So in this equation you see that we have effectively adopted the Bernoulli equation in order to find out the pressure gradient. Okay. We will continue to see some few simple problems. Again now concerning application of your Bernoulli equation, this is a small very simple problem. Say diameter is given as 20 centimeters and specific gravity is 0.9, then you have discharge rate equal to 120 liters per second. So at any point, so this is the datum, at any point A which is 4 meters above the datum line, and here the gauge pressure is given as. So calculate the total energy at this point in meters of oil. It is a very simple problem. So you know the total energy is P by gamma V square by 2G plus Z. So P by gamma is nothing but, you have this you need to convert it. So this will be point specific weight. So specific gravity also has to be taken. So this will come to 1.88 meters of oil. So that is the potential head. Then you have to calculate here, because the Q is given. So Q is can be written in terms of in terms of meter cube per second, as it is given there. So that will be, and then area of cross section can be obtained, because this is 0.2 meters. So you have Q is calculated, Q is converted and A is calculated, and so velocity can be calculated as Q by V, Q by A. So the velocity head will be 4 meters per second. Okay. So velocity head will be V square 2G by V square into divided by 2G. So that will be the so the total head will be pressure head, that is 1.88, then plus V square by 2G, V is already known, plus you have to make sure that you include this datum head, that is 4 meters. So you will get that as 6.69 meters per oil. So this is a very simple problem. So you know next is, this is the next problem. So read the problem, keep reading the problem and try to understand what the problem tries to ask you. A 20 centimeters diameter pipe, so dia is 25 centimeters or 0.25 meters. Then water velocity is 25 meters per second, that is the velocity at any point A. At a point A, measurement of pressure and elevation. So pressure is 3.7 kg per centimeter square, and head, let me call it as, is okay. The pressure at some other location, that is B. So this is A. So here B is 32.5 meters, and your this one is 3.6 kg per . So for a steady flow, find the head loss between A and B. So this is A, the details are given here, and this is B, details are given there. So you use the total energy as per the Bernoulli equation. So at point A, you can calculate with this data, that will be 37.7 meters of water, and with the velocity you can calculate the velocity head, and the elevation is given. So, the total energy will be, total head will be 100.6 meters. At point 2, in point B, this is P by gamma can easily be calculated. So, V square also can be calculated, then you have this one. So, the B will be equal, at B the total energy head will be 9.96. So, you see that the head loss will be this minus this, which is 4.5 meters total energy loss. Okay. See, all these things are quite important, particularly when you are working with the flow problem, flow related problems. You need to use some of these calculations. Then next is a conical tube is fixed vertically with its small small vertically down. So, the smaller end is upwards. The velocity at the velocity down the tube is 4 meters per second, 4.2 meters per second at the upper end, and at the lower end it is 1.72 per second. So, the length of the tube is 2 meters, and the pressure head at the upper end is 2.85 meters. Now, the loss in the head is expressed, so the head loss is expressed as 0.3 into V1 minus V2 whole square divided by 2g. So, where V1 and velocity, so this will be V1 and this will be V2. Is that clear? So, what is the pressure? So, we have all the details. What is the pressure head at the lower end? So, the pressure head here is given, velocity head is given, velocity head at this end is given, but you are also given the head loss due to friction. So, what is the pressure head at this end? So, usually the problems will be related like this. So, according to the the moment you apply the Bernoulli equation for these two ends, so this is the left hand end, and on the right hand side you will have plus the head loss due to whatever head loss, it may be due to so many factors. Is that clear? So, from this what we need is, from this equation what we need is P2 by gamma, this is what we need. So, if we simplify this, and this is the final expression. So, P1 by gamma is calculated, already given, then Z1 minus Z2 can be calculated, that is 2 meters the difference, then V1 is already given, V2 is given. So, substitute in that expression, so you get P2 by gamma, that is the pressure head at this location, as 5.5. Now, we will just try to familiarize ourselves with this application of irrotational conditions, then the velocity potential calculations, the meaning of velocity potential, the meaning of stream function, etc. through I think I should have about 2 or 3 or 4 problems, I would guess 3 or 4 problems. So, with that we can complete the basics of fluid mechanics. Any of you have any doubts? It's all quite straightforward. Okay, in this problem a 3-dimensional flow is considered. So the velocity components in any of the two directions are known to us. So we need to find out the other component on the assumption that it satisfies the continuity equation. So u is given and v is also given as, so there is one more problem. So first I will explain the first problem. So dou u by dou x you can calculate, dou v by dou y, that is calculated. So you know that the continuity equation so we need to know this, because this is known, substitute in this equation which is the continuity equation, and then you will get dou u by dou w by z equal to so much, and integrating both the sides you will get this one where c is the constant of integration. So in the same way you need to do the next problem, dou u by dou x. I am talking about these two problems. Here in this case you are supposed to find out the velocity in the y direction. So this one is known, then dou w by dou z. So look at this, there is no term in z, so this will become 0, dou w by dou z, okay. And then substituting the above, so the two components your derivatives you have found out, then substitute in the integration and then integrate both sides, you will get the velocity in the y direction, okay, where c1 is the constant of integration which is going to be function of z and x. Okay. So in the same way here there are two components which are given to you, u and v. Show that these functions represent condition, I mean irrotational flow, and you are supposed to get an expression for stream function. So dou u by dou v, dou u by dou x and dou v by dou y are obtained using those two expressions. Then you add these two, so that can be expressed as shown here, so that satisfies the continuity equation. So it is just checking the satisfy whether the two flow fields flow components are satisfying the continuity equation. Then you calculate your, further you can also find out the dou v by dou x, dou v by dou x and dou u by dou y. So that is one of the conditions for irrotational flow. So once you do this you get that this is going to be 0. So that means the flow is irrotational. Now dou psi by dou x, we have already calculated we already know the expression for v. So now you can get dou psi by dou x equal to v. So you get an expression there, and similarly you get an expression for dou psi by dou y, which is dou psi by dou y is nothing but minus u. Is that clear? So once you have got this, so from the integrating, so from this equation you get, so let me write this for you. Whereas this will be okay. So let me call this as equation 1 for this problem alone, so it is easy for you to understand. So now integrate this one. Once you integrate this, what are you going to get? You are going to get psi. So integrate this and you are going to get the expression for psi, which is this is expression for psi, and this is the integration constant, which is going to be a function of y. Then differentiating equation 3, if you differentiate equation 3 with respect to y, then you get dou psi by dou y is equal to this much. Okay, you just simply differentiate this, but this we have already got here. So you equate equation 2 and this equation 4, so that you get an expression for y fy dash. So then you put all these things, substitute the numerical, so substitute for f dash y, so you get the expression for psi with a constant of integration, numerical constant of integration, which may also be considered as 0. So this problem explained to you. So with this, I think we have touched upon a few sample problems on basic fluid mechanics, and then with this background knowledge, I am sure this is the main information which you might be needing. Apart from there may be some other informations also which we will be touching on while dealing with the wave hydrodynamics. So with velocity, potential, stream function, all these parameter, all these functions will be considered while dealing with the subject on wave mechanics. So any further questions on this? Close.